We're going to be using these videos as introductions to each unit, so they'll provide you with notes and some formulas that you'll need for in-class discussion. Viewing these videos will provide you with some basic terminology and some basic definitions that I'll be using in class that I may not review. I'll be expecting you to just know. So make sure you take the time to listen to the videos and take notes on what you need. I'll hand you out a copy of the video, almost like a script, the night before you have this as an assignment so that you can use it to take notes on, so you won't have to copy it at home. But it's important to watch the video because a lot of times I discuss certain things that are not necessarily on the paper, but that I want you to understand. So this first video is for Unit 1 for kinematics. Some of the objectives we'll have for this unit are to define what motion actually is, how is it characterized, and what are the basic variables that come into calculating motion and describing motion. We're going to understand what acceleration is and motion on an inclined plane. An inclined plane is a ramp or some type of inclined surface that allows things to roll down it. And we're going to understand motion from different perspectives or frames of reference. A frame of reference is like trying to describe something if you're the passenger in the car and you see a bird fly by, or if you're somebody standing on the side of the road observing the same bird. There are different perspectives or different things that you see. So in physics, a lot of times your variables will change, or they'll be changing different frames of reference that will affect your problems. So first, how do we define motion? There's two ways to talk about motion. There's kinematics and dynamics. Kinematics is what we will start with for the first two units. Kinematics is a study of calculating motion without the concern of what causes it. So it's not like I'm running down the hallway thinking about what's causing me to move. It's more like I'm traveling at a certain speed in a certain direction. So I'm going 50 miles an hour down the highway. Nothing describes why I'm doing it or what's causing it. It's just the measurement variables that I can have of that motion. So how long did it take me to get from here to there? It took me 20 seconds. It doesn't tell me what caused me to move or why I moved. It just measures the movement itself. So that's what kinematics is. And if you think of the word kinematics, kinetic is your basic root word in kinematics, and that means motion. So this first unit, the first two units actually, will discuss the measurement of how things move. There are two ways to measure kinematic variables, and we're going to have another slideshow that will, during Unit 2, go a little more in depth into one of these. But the two ways to measure kinematic variables are scalar quantities and vector quantities. The difference between the two is that scalar quantities have only magnitude. They have magnitude only, which is like distance. I walked 50 miles. It doesn't tell me anything except how far I went. That 50 miles could have been in a circle around my classroom, or it could have been in a straight line down the road. It could have been zigzag back and forth through a field. That stuff's not given to me, just the distance. Or speed if I'm going 20 miles an hour down the highway. Or a mass of an object, or time, 50 minutes. It doesn't give you anything else except a strict magnitude measurement. Vector quantities give both magnitude and direction. So these include quantities like velocity, displacement, and acceleration. Velocity tells me either an angle in which I'm traveling at. For instance, if I'm traveling northeast, that gives me an angle, or if it's at an angle of 30 degrees, that gives me an angle along with that velocity. Displacement tells me the same thing. If I'm traveling 50 miles from Massachusetts to the coast of Maine, from here to here, it gives me a direction as well. So that would be displacement. And acceleration, since it's the rate at which velocity changes and another rate of displacement, carries along that vector quantity. And you're going to see that acceleration you actually can experience in two different ways. So let's get some definitions of some of these basic vector quantities. Displacement is the distance traveled in a straight line from point A to point B. So some cliche terms you have for displacement: as the crow flies. If a crow flies, it flies above the trees in a straight line. Or a beeline is the line from a bee to its hive. A lot of times you'll hear it, I made a beeline for the door, things like that. It's a straight line or a straight shot. It's represented with the lowercase variable, lowercase d. Don't capitalize that. Capital D could be used for density or other variables. We use lowercase d for displacement in this unit. The units that we're going to use are the SI units, and that is metric. And we'll use the metric system, which is meters, and we'll use the metric system for our entire course, unless otherwise specified. Now we're going to be dealing with what's called linear kinematics. So linear kinematics means on a straight line, which means we don't necessarily have directional values. It's on one single straight line, there's no left or right, up or down. So a lot of times you'll hear me say distance or displacement, but in the first unit, distance, displacement, velocity, and speed, they're interchangeable. So I could be saying distance, but I mean displacement as a vector. So remember that. It does not have the directional value, so they'll be interchangeable. Velocity is the rate at which displacement changes over a time interval. It's speed with a direction. It has a directional value. So 50 miles an hour northwest has a directional value. You'll see this if you're on the highway, you look at your speedometer, it only tells you how fast you're going. But if you've got one of those compasses on your rear view mirror, you now have a vector. You now have a magnitude and a direction. Usually in this class, we're going to use a degree angle made with the x-axis. So something like this, like 30 degrees. Or if I'm traveling on a map, that 30 degrees would be one of my directional values, and it looks like I'm going northeast. Or if I'm launching a projectile, that's an angle of elevation from the ground. But a lot of times we use a directional value from the x-axis. Now remember, if you're using a calculator, you want to be in degree mode. You could be in radian mode for math, but that will set off your calculations in this class. We're always in degree mode. So the variable for velocity is a lowercase v, not a capital V, because that is for volume. And since we're in the metric system and it's a rate at which displacement changes, if displacement was meters, then velocity is meters per second. In the English system, you'll see it as miles per hour, feet per second, but in physics, we're going to use meters per second. Acceleration is the third variable that we'll be using for vector quantities. And velocity was the rate at which displacement changed. Acceleration is the rate at which velocity changes over time interval. It too has a directional value, and it is also made with a degree from the x-axis. And there's different ways of discussing acceleration. You can have a positive acceleration, which either means a directional value, if you've established traveling to the right as being positive and you're accelerating to the right, it could be positive. Or it could also be speeding up, going from a lower velocity to a higher velocity. You could have a negative acceleration if you're going in the opposite direction, or if you're slowing down, going from a high velocity to a low velocity. Your acceleration variable is a lowercase a, and since it's a rate at which velocity changes, and velocity was meters per second, it's meters per second per second. Now, if your time variables match, they can be reduced in this to meters per second squared. However, if they don't match, if this was like, say, meters per second per hour, you would have to keep it in that original form. But generally, we're going to convert everything to meters and seconds, so we'll be using meters per second squared as our basic acceleration unit. Now, by speeding up and slowing down, as I had stated earlier, you can feel accelerations. If you're in your car at a stoplight, and you hit the gas when the light turns green, you're going to feel like you're pushed back in your seat, but you're not actually pushed back in your seat. Your car is speeding up, and the back of the seat is coming forward to meet your body. So you're not actually going backwards. Your car is going forwards and meeting you. So you can feel that acceleration. You feel it on a roller coaster when your stomach goes all over the place because you just dropped down a hill. The slowing down is the same thing. You hit the brakes and you feel yourself going forward. You're not actually being pushed forward into the car. You're still traveling and the car is slowing down, which means the front of the car is coming backwards to meet you. And you can feel these two. Another way of feeling an acceleration is not a speed change, but a directional change. If you're traveling in this direction and your car goes left, you get pulled into the right side of your car. So you feel like you're going to the right, when in reality you're going straight and your car is turning into you. Same way if you turn left, if your car turns right, you feel like you're being pushed to the left, but in reality you're going straight and your car is coming to meet you. So you can feel acceleration as either a speed change or a directional change. There's two ways to feel it. In physics, we use a lot of equations to help us solve for variables and to describe motion that's occurring. For kinematics, we're going to use several variables that will help us solve for missing variables or objective variables, and it's also going to describe the motion. We'll be able to use these for graphing as well. We're going to have variables and equations that are dependent or independent of a time variable, and we're also going to use these equations to solve for objects moving at constant acceleration in a straight line, especially on an inclined plane. So as we go through here, what you should do is set up a separate sheet of paper to record the formulas that I give you. They'll also be recorded on the board in class, so you won't need to memorize them for tests. The assumption is that you'll have used them enough that you will remember them and you won't need to reference the board. However, I will write these formulas on the board as we use them in class, but it's definitely helpful to have your own separate list. So like I said, this list just reiterates it. Use a separate sheet that you can use for homeworks, and you'll have the equations on the board for tests. So the first equation is for average velocity. Remember, this is linear kinematics, which means we're on a straight line. So you'll hear me say speed and velocity or distance and displacement interchangeably. That's okay, because right now we're not dealing with directional values. I'll try my hardest not to, though. So velocity is the rate at which displacement is changing over a time interval. So if we write it, velocity is displacement over a time interval, 50 miles per hour, or 10 meters per second. It's a rate at which my displacement is changing. Now, we use subscripts in physics a lot to describe things. So this AVE is average, so an average velocity. You'll see a lot of subscripts in this class, I's for initial and F's for final and 1's and 2's and all kinds of subscripts. Don't use the subscripts for mathematical work. They're just descriptions. So I'm not actually multiplying V times A times V times E here. It's just my velocity vector with a description underneath. So, by writing my velocity average as displacement over time, I have my first average velocity formula, but I'm going to rearrange it into a kinematics formula. I'm going to multiply time to both sides so that what I get is distance equals velocity times time. This is the formula for my average velocity, and this one is very important. It is the basic formula for kinematic motion, and we're going to be using it to evolve it into larger formulas that include more variables and more descriptions of motion. But this is a very basic motion. This would be the first formula that you would write down on your list. There's another way to write down average velocity as simply an average. When you average something, you add all the parts together and divide by the number of parts. We need to establish descriptive subscripts for this one. So a VI with a subscript I is an initial velocity, what I start out at. A lot of times you'll see in your physics text it's written as V0. That 0 is your naught variable. It's written as like V naught or T naught. It's an initial starting variable. So in class I use initial and final because I think it's a more agreeable variable for us at this level, and a lot of times books you'll see use that. I may use a 1 or a 2 for a first and a second, but it still describes the same thing. It doesn't change the variable. So unlike the first formula where we have an average velocity and a time and a distance, now we're using multiple velocities and we're going to average them together. So like I said, to take the average of something, you add them together and divide by the number of parts. So VAV is also equal to final plus initial velocities divided by 2. So if I'm going 40 miles an hour and then 60 miles an hour, my average is 40 plus 60 divided by 2 is 50 miles an hour. My second equation is for acceleration. Velocity was the rate at which displacement changes. Acceleration is the rate at which velocity changes over a time interval. It can be written as acceleration is a change in velocity. That's what delta means. The delta symbol equals a change. So this is like a change from your final and your initial. You can see it down here. And that's over your time interval. So my change in velocity going from one to another, it's kind of like what we do with classic muscle car type measurements. My car can go from 0 to 60 miles an hour in 5 seconds. It must be a great, actually that would be a pretty bad car. A sports car can go from 0 to 60 miles an hour in 3 seconds. That would be a really fast acceleration rate, or really high acceleration rate, and a really large change in a certain time interval. So that 0 miles an hour would be my initial velocity, the 60 miles an hour would be my final velocity, and the 3 seconds would be my time to give me an acceleration rate. If I now substitute the VF minus VI into that acceleration formula, I get A equals VF minus VI over T. This is an important formula for us to have because it now involves two different velocities, time, and acceleration for one simple concept. So those are the basic equations that define motion. What we're going to do is combine them into two master formulas, a time-dependent and a time-independent motion equation. We're going to be able to use these equations to calculate an object's motion with or without the use of time, and we can use them many times for simple formulas because a lot of the variables may equal 0 and cancel out part of the equations. But first, we have to derive these larger formulas. So you have to be ready and you have to keep up because it's going to go quickly. So the first one, the time-dependent motion formula, you have to have the time variable. So I'm timing something as it travels. I'm going to start with my basic distance equals velocity times time formula. And what I'm going to do is a series of substitutions that allow me to get initial and final velocities in here, acceleration, all the other variables built into this equation. The first thing I'm going to do is I'm going to substitute for average velocity the formula I had earlier, VF plus VI over 2. So I'll substitute that into the equation to get my VF and my VI variables in there. My next step is to substitute my final velocity variable in order to get acceleration into the equation. This formula, the time-dependent motion formula, is really kind of like I start a race and I take splits all along the race as I go, 20 feet, 40 feet, 60 feet, and so on. So it doesn't really have an ending. It's kind of an evolving formula. You start the time and you let it go, and you can stop, you can stop, you can stop whenever you want, but there's no final velocity. This formula originates from A equals VF minus VI over T. I multiplied time to both sides, and then I added the initial velocity to the acceleration side to isolate the VF variable. I'm then going to take this section right here, the VI plus AT, and I'm going to substitute it in for VF from the other formula. So I have D equals VI plus AT plus VI over 2 times time. I have all the variables now, but I need to clean it up. I want to simplify this formula. So the first thing I'm going to do is I'm going to take that divided by 2 out of the formula. Remember, this whole thing was divided by 2. I'm going to multiply the whole thing by a half. That'll get the 2 out of the denominator. I'm also going to add the two VI's that were originally in this formula together. So instead of having VI plus AT plus VI, I'm going to have 2 VI plus AT. That's my first step. Second step is I'm going to multiply time into the parentheses. So both of these, the 2 VI and the AT, will be multiplied by this time variable on the outside. So I get 2 VIT plus AT squared. So it produces this square here. Next thing I'm going to do is distribute this 1/2 through to both of these. So 1/2 times 2 equals 1, so I'm left with just the VIT. and 1/2 times at squared gives me 1/2 at squared. This is the time-dependent motion formula, d equals vit plus 1/2 at squared. You can see a lot from this formula. If I start at an initial velocity of 0, meaning I'm starting at rest, this whole section right here goes to 0. It's all gone, and I'm left with my acceleration rate and the time I accelerate for. If I'm not accelerating, this whole section right here with the acceleration goes to 0, and I'm left with just d equals vt, an average velocity, because I'm not accelerating or changing my velocity. So it has all the variables in there, and I can use those variables to solve this master equation, as long as I have a time variable. Now that we have a motion formula that depends upon time, it's time, no pun intended, to get a motion formula that does not depend upon time. So let's say we forgot our stopwatch and we have no other way of measuring time. We can use this motion formula to get some of our variables like acceleration, displacement, and our velocities. So again, we're going to start with our initial d equals vt average velocity formula. And we're going to make a series of substitutions, but this time we have to isolate the time variable and get rid of it. We also have to incorporate acceleration in here. So again, like last time, I'm going to substitute in for average velocity, my average velocity formula to get vf and vi in here. So vf plus vi over 2. And same thing as last time, my a equals vf minus vi over t formula. I'm going to rearrange it. I'm going to multiply both sides by time, and this time I'm going to divide both sides by acceleration. So it's basically swapping my time and acceleration variables here. So I've isolated my time variable, and I have my vf, my vi, and my acceleration. And I'm going to substitute that time variable in for where it was in the original equation. So now I have two fractions that I have to multiply together. Now I have all my variables. Again, I just need to simplify. The first thing I'm going to do is I'm going to multiply both sides by 2 and both sides by a, which will get them out of the denominator and bring them over to the other side. So I have vf plus vi times vf minus vi, right here, equal to 2ad. And this, if you notice, is the difference of two squares. This is your a plus b times a minus b. It's one of those algebraic formulas that lets you FOIL those multiplication factors, and what you end up with is vf squared minus vi squared equals 2ad. And this does not involve time, but it still has an initial and a final velocity, an acceleration, and a displacement. You notice now we have a final velocity to deal with. So it's like going from 0 to 60 miles an hour in a quarter mile. So I have a definite starting and ending point, and I don't need time for this. Now, an interesting thing to look at is how the units work for this. Velocity for vf is meters per second, and that's squared, minus vi velocity is meters per second, and that's also squared, equals 2. Acceleration is meters per second squared, and displacement is meters. So if you look at this closely, this meter multiplied into this one gives me meters squared over seconds squared. And when I square these velocities, what I end up getting is meters squared over seconds squared. Meters squared over seconds squared. So the variables on both sides are actually the same. Meters squared over seconds squared and meters squared over seconds squared. So the units also work as well in these formulas. So here's a final list of the equations that I will be putting on the board for you. You should also keep them in a separate sheet, maybe in your workbook, in the inside cover of your workbook, or on a separate sheet in your notebook, so you can access them anytime you need to for labs or for homework assignments or anything that you may have taken home with you. After this video, the example video will be up shortly to show you how to use these formulas in actual physics equations. A lot of times you're going to see that you'll use one formula, for instance this formula, to calculate for a variable. You'll use in this formula to calculate for a different variable. So you have to get used to these formulas and how they work, or these equations, and be able to use them in conjunction with each other.